Hello, and in this session, we're going to be speaking about recurrence relations. This problem uses recurrence relations in a linear search. Our input is an array A of n distinct integers and an integer k. We output yes if k belongs to A, else output no. So if there's only one element in A, we return whether that element is equal to k. Yes if it is, and no if it's not. This takes O of 1. Else, we check if the last element is k, and after that, we repeat the process for all the elements except for the last. This is called the inductive hypothesis, and it takes a total of t of n minus 1. So as a result, we can write t of n is equal to O of 1 if n equals 1, and c plus t of n minus 1 if n is bigger than 1. Now, let's solve this recurrence. We know that t of n equals t of n minus 1 plus c if n is not equal to 1. Hence, we can write it as t of n minus 2 plus c, and so on until we get t of 1 plus c plus dot dot plus up to c, n minus 1 times, giving us O of 1 plus c of n minus 1, which is equal to O of n. Okay, now let's see how it applies for an insertion sort. Our input is an array A of n distinct integers. Our output is a sorted array. Let's take a function that takes t of n time in total. If there is only one element, then we return the array A. Else, we use recursive call to put the insertion sort function of the first n minus 1 elements into A prime. This takes t of n minus 1 time. Then we insert the last element into its appropriate spot in A prime, which takes O of n time. So as a whole, t of n is equal to O of n if n equals 1, and if n is bigger than 1, it takes t of n minus 1 plus O of n time. Okay, now let's solve the recurrence. T of n equals O of 1 if n equals 1, and equals to t of n minus 1 plus cn otherwise. So t of n is equal to t of n minus 1 plus cn, which we can expand into t of n minus 2 plus c times n minus 1 plus cn, which goes all the way to t of 1 plus 2c plus all the way to cn, which is equal to O of 1 plus 2c plus all the way to cn, which is equal to O of n squared. Now, let's do a problem relating the powers of 2. Our input is a non-negative integer n, and our output is 2 power n. Let's take a function that takes a total of t of n time. If n equals 0, then we return 1, which takes O of 1 time. Else, we recursively call n over 2 and put it in temp, which takes t of n over 2 time. If n is even, we return temp times temp, which is an O of 1 time. Else, we return 2 times temp times temp, which also takes O of 1 time. For simplicity, let's assume that n is an exact power of 2 and continue on from here. T of n is equal to O of n if n equals 1, and is equal to t of n over 2 plus O of 1 if n is bigger than 1. Now let's solve this recurrence. T of n is equal to O of 1 if n equals 0, and equal to t of n over 2 plus c otherwise. Since t of n equals t of n over 2 plus c, t of n is equal to t of n over 4 plus c. This goes all the way to t of n equals t of n over 2k plus c times k. This stops when n over 2k equals 1. Solving this, we get k equals log 2n. Hence, t of n equals O of 1 plus log 2nc, which is equal to O of log n to a base 2.